Okay, excellent. Hello, my name is WBain, and over the next 5 minutes, I'm going to tell you a little bit about the work that I've been doing for my postdoc in looking at a mafic ultramafic complex that's located about 2 hours north of Thunder Bay in northwestern Ontario, called the Legris Lake system. Legris Lake is one of several mafic ultramafic complexes that it's located along the boundary between the Wabigoon and Quetico subprovinces, and is one of a circular array of complexes that has a unambiguous spatial and temporal relationship with the lactosile system. That spatial and temporal relationship has led to a hypothesis that all of the mafic ultramafic complexes in the system have a genetic relationship to one another. And so one of the objectives of my project is to evaluate how the Legris system, how the geology and geochemistry of the Legris system and of these satellite intrusions relates to the lactosile system. On the right-hand side of the slide, I've just shown a geologic map of the Legris Lake Complex. This complex is mostly a gabbroic composition and consists mostly of plagioclase and plagioclase CPX cumulate rocks. The part of the system that's really gotten a lot of attention from the exploration industry is just shown here in the top portion of this map. It's called the Northwest Border Zone, and this is an area of the system that contains contains the main focus of sulfide mineralization. A really important detail about the Northwest Border Zone, as well as the complex generally, is that there's a lot of evidence for interactions between the silicate melts in the system and the local Quetico metasedimentary rocks. And I've just shown some pictures here on this slide. The evidence for these interactions includes things like roof pendants that have really unambiguous textures that are indicative of partial melting, as well as sedimentary xenoliths that have also textures that are indicative of assimilation by the system. And as we'll see in the coming slides, this sedimentary rock assimilation is something that really has a strong control in the geochemistry of the system. When we look at the whole rock geochemistry of the complex, generally speaking, it's kind of impossible to interpret the whole rock geochemistry without kind of accounting for metasedimentary assimilation. I've just shown that here on the left-hand side of this slide. This is showing some of the whole rock geochemistry just from the complex generally, and for the most part, most of the data points coincide with a tie line between plagioclase and a mixture of pyroxenes that's about 60-40 CPX to OPX. But also we see in the geochemical data that there's kind of like an upper and a lower array. And to understand those upper and lower arrays, we kind of have to look at the effect of metasedimentary assimilation. I've just put or I've overlaid a field that just shows the composition of the metasedimentary rock. You can see that this lower array is coincident with the composition of the metasedimentary rock. If we were to look at a spatial plot of the data points, we see that this lower array is also coincident with these data points that are shown here circled in red for this upper array, and also that these data points coincide with the areas that are really enriched in sulfide mineralization. So from that, we can interpret that this metasedimentary assimilation is itself associated with the precipitation or the formation of sulfide mineralization in this system. It also coincides with a shift in the chemistry of the system from a composition that's mostly plag and CPX rich to a composition that's mostly calcium rich plagioclase and OPX rich. So that shift in the mineralogy is associated with the formation of sulfide mineralization in the system, as well as with the assimilation of metasedimentary rock. In this slide, I've just shown that the assimilation of metasedimentary rock also has a huge effect on the trace element chemistry of the system. And if you look down here in the right-hand side of the slide, I've just shown the composition of the main mineralized LGAV in this system, and you'll see that the upper limit of its variability is essentially defined by the composition of the local metasedimentary rock, or the MTSD. And I did some just simple mixing models between primitive mantle and the composition of MTSD, and found that in the areas that have a lot of the mineralization, that amount of metasedimentary assimilation is about 40%. So looking at the trace element profiles of the various cumulative lithologies in the system, I picked a number of those profiles that showed the least amount of evidence for metasedimentary assimilation, and used a equilibrium distribution model of Bedard 1994 to model the parental magmas, or the trace element content of the parental magmas in this system. And I've just shown the results of that modeling here in green. And the trace element, the modeled trace element profiles indicate that the melts in the Legris system formed by low degrees of partial melting of a metasomatized mantle source and in a continental arc setting. And just to hammer home that last point, I've overlaid the trace element content of just kind of like a model continental arc gabbro here. And you can see that the modeled trace element profiles are very much in agreement with that. Also, I've put a modeled melt profile for a more evolved unit that's inside of the central portion of the Legris system, the LGAB bio, and that trace element profile indicates that the assimilation of metasedimentary rock has actually caused the system to become more fractionated, and that's just expressed by the distribution of these data points at much more fractionated compositions. In order to look at the effect of crustal contamination in the system a little further, I took a look at samarium and neodymium isotopes. And in the Legris system, the SMND, or the epsilon neodymium signature, ranges from 0.28 to 1.34. And that's a range that's indicative of a mantle source, but also the variability, or the wide range of the values, is also indicative of mixing between a mantle and a crustal source in this system. And the obvious choice for the contaminant is that local metasedimentary rock. However, I'll point out that the range in samarium neodymium isotopes from Legris is almost exactly that of what we see in the LDI system. And there they've interpreted that range in epsilon neodymium values to be related to assimilation of tonalitic country rock at depth. So there's also the possibility that that's going on inside of the Legris system as well, given its close spatial association with LDI. So to take a look at the country rock assimilation a little bit more and its effect on sulfur isotopes in the system, I did a multiple sulfur isotope study of the sulfide mineralization in the Legris system, and I've just shown the results here on the right-hand side. Indeed, the comparison with the sulfur 34 isotope ratio and the ratio of sulfur to selenium, we see that the data from Legris are mostly within the mantle array, but skew towards more positive values, indicating the addition of crustal sulfur. And that last point is really emphasized by the delta 33S isotope ratios, which are consistently negative or non-zero values, indicative of interaction with Archean crustal material. And all of that taken together, or rather, when we look at the sulfur isotope signature in the metasedimentary country rock, which is shown here by these red circles, we see that the data from Legris encapsulate that sulfur isotope signature in the metasedimentary country rock, indicating that the full variability in sulfur isotopes can't really be accounted for by simple assimilation of MTSD, and that suggests that another contaminant is the likely source of external sulfur in this system. And we're interpreting that to be related to tonalitic country rock assimilation at depth. So just to bring it home, my model, or my working model for the Legris system, involves a staging chamber that's at depth, in which you're getting assimilation of tonalitic country rock and sulfur saturation at depth, and magmas that are saturated in sulfur are variably sampled by the injecting magmas that are forming the Legris complex, and in turn, as those magmas are intruded, they're assimilating metasedimentary country rock, and that, together with the tonalite country rock assimilation, is driving a shift in the mineralogy towards more calcium-rich plagioclase and OPX, and at the same time, the precipitation of sulfide mineralization. Thank you so much.